depending on yesterday experience, people travel between, yeah. So we, the program delayed 10 minutes, sorry, tolerate. Okay, yeah, maybe we can start. It's my great pleasure to introduce Professor Mikhail Belolipetsky, sorry for my pronunciation, from IMPA, Brazil. Let me just briefly say, Professor Belolipetsky research interest is in arithmetic groups and their geometric properties, representation theory, and number theory, and hyperbolic geometry. He got his PhD in 2000 from Novosibirsk State University, Russia. His title is Hyperbolic orbifolds of small volume. Before I conclude my introduction, I'd like to present a gift from ICM organization committee to Professor.
I'd like to thank the organizing committee for an opportunity to speak at the ICM. My talk is about hyperbolic orbifolds of small volume. So the plan will be, I'm first going to explain a little bit why we are interested in volumes of hyperbolic manifolds and orbifolds. Then I will show some results, and at the end I would like to talk about some geometric problems, most of which we don't know how to solve. But the results which I explained will give some strong indication and conjectures in geometry. So let me start. To those who attended the previous lecture by Professor Planck, you have to switch very quickly from non-negative curvature to negative curvature. And what's going to happen is that you will notice a lot of parallels, like tools reappear. However, geometric intuition is totally different. So what you see geometrically in positive curvature, you're not going to see negative curvature, vice versa. So geometrically, it's another world. Well, I'm going to talk about hyperbolic manifolds. So what are hyperbolic manifolds? We start with a n-dimensional hyperbolic space. For example, you can think of an upper half plane with a hyperbolic metric and its group of isometries. Now if we take any discrete subgroup of the group of isometries of the hyperbolic space and consider the quotient space, then, okay, in general it's going to be hyperbolic orbifold. So it inherits the constant negative curvature metric from the space, but if group gamma has elements of finite order, then this quotient space will have singularities. And it also may have cusps if gamma has parabolic elements. However, if gamma is torsion-free subgroup, then M is a manifold. So it's a constant curvature -1 n-dimensional manifold. I'm going to talk about finite volume hyperbolic manifolds and orbifolds. So why are we interested in finite volume spaces? There are several reasons. There are more than several reasons. I will just mention a few reasons to give you the idea. So first, let's recall the Schoen-Gauss-Bonnet theorem, which says that in even dimensions, we have a relation between the volume and Euler characteristic of the space. So volume defines Euler characteristic, and Euler characteristic is well-known topological invariant, which captures a lot of important information about the space. So volume does the same. However, in odd dimensions, Euler characteristic vanishes, and volume is still well defined. It actually captures the same amount of information. Next property is the celebrated most of Prasad rigidity theorem, which tells us that volume is a topological invariant. So, well, what it means? So, well, in this case, the topology of the space is actually defined by its fundamental group, and it says that the volume is invariant of the fundamental group. But the point is that volume is just one real number, and fundamental group is some countable non-abelian group, some very complicated object. So we assign this invariant to any group of hyperbolic transformations or any hyperbolic orbifold, and one number captures some amount of information. Apparently, it's a lot of information which is captured by the volume. So it's very powerful invariant. Well, one other property which I can mention is that so there is another invariant which is called simplicial norm, or Gromov-Thurson Gromov norm. It's a measure of complexity of the minimal triangulation of the manifold. So the theorem of Gromov and Thurston says that the volume is proportional to simplicial norm. And therefore, volume is also a measure of complexity. Now, well, here is a picture. So these are nodes, and we know that most of the node complements are hyperbolic, in the sense that if we consider a node in three-sphere, consider its complement, then except two well understood special cases, almost all nodes complements will have hyperbolic metric of constant negative curvature, and we can compute the volume of this complement space, which is non-compact but finite volume. And so volume is an invariant of the node. More classical invariant of the node is, of course, the minimal crossing number of the node diagram. And this is how nodes were organized in Ronson's book and earlier. So this is classical approach. But in a celebrated paper from 1999, Biggs, Callahan, and Dean presented a table which orders nodes by the volume of its complement. So the simplest node is figure 8 node. And then it goes, and you see that volume of the complement is very deep. So node can have quite a few crossings, and this has many crossings, but this has smaller volume. But apparently volume is a better measure of complexity by various reasons. But it's less intuitive in this case. In this picture, in the first page of the classification, they classified nodes up to a certain volume, and then there are several other papers which I mentioned in proceedings, paper which enlarged this list. But another interesting fact to mention is that most nodes complements have different volume. So in this first diagram, only two nodes, these two, have the same volume. And when you go further, apparently it's a very effective way to distinguish nodes. You just compute the volume of the complement, which computer program by Jeff Wicks can do for you, and it normally distinguishes them. Or not always, but works quite well. Okay, let me also mention that this node, figure 8 node, is arithmetic node, and arithmeticity will appear more in this talk. So in his lecture, Jan Egel mentioned Thurston's famous problems from the Bulletin of OMS article. There were 24 problems there, and 23 of the 24 problems are some problems are very abstract, but basically 23 are solved, and one remains open. So this remaining problem show that the volumes of hyperbolic three manifolds are not rationally related. And since 1982, we apparently don't have any progress about this problem, unfortunately. So what we know is that for even dimensions, volumes are of course rationally related by Gauss-Bonnet theory. And the conjecture says that in odd dimensions, the situation is different. So if we restrict to arithmetic manifolds or orbifolds that I'm going to define very soon, then this problem is related to deep open questions in number theory about rational independence of zeta values. There was a beautiful talk yesterday by Francis Brown about periods and relations between zeta values. However, well, there was spectacular progress recently, but it's in different directions. So this direction is completely unreachable so far. There is another problem, also well known, minimal volume problem. So it says that show that the volume of hyperbolic orbifolds is bounded below by a constant which depends on the dimension. This goes back to a paper by Siegel, who raised this question and showed the solution for n equals 2. In fact, that solution can be traced back to a paper by Hurwitz, who also found the same example, 237 triangle, in connection with different questions, automorphisms of Riemann surfaces. This problem was solved in general for all the groups by Kazan and Margulis, who proved the existence of lower bound. However, the bound, so I will talk more about this at the end, but the bound in Kazan and Margulis' paper is computable, and we now know how to compute it, thanks to, in particular, the work of Adeboye and Wei. However, it's very far from precise. So I don't have any reason to expect that the bound which you get from the proof of Kazan-Margulis theorem will be sharp. In fact, it's very, very far from the actual minimal volume. So what I would like to talk about is my paper in our joint work with Vincent Emery, in which we solved this problem in a special case of, again, arithmetic hyperbolic and orbifolds for arbitrary dimensions starting from 4, and the solution for dimensions 2 and 3 was already known. Dimension 2 is classical, due to Ziegler, and dimension 3 is work by Friedman, Chinburg and Friedman. So I will mainly talk about this result and some of its corollaries. Now I need to tell you what this arithmetic is. I will start with example. It's a very classical. So look at hyperbolic plane and look at modular group. So it's group of 2 by 2 matrices with determinant 1 integral coefficients. It's obviously discrete subgroup of the group of isometries. What is less obvious but well known is that it has finite coarea for volume. So the thing is that this group is not co-compact. Its fundamental domain is this half strip. It's infinite, but because of the hyperbolicity, when we integrate along this fundamental domain, we get a finite number. And this is the volume, the area in this case. So the quotient space is a sphere with 2 singular points, 1/2, 1/3, and 1 cusp. So it's a non-compact hyperbolic orbital. And here are 3 ways how to compute its volume. The first, as I mentioned, we can integrate the volume form on the fundamental domain. The second is the easiest one in practice. In this case, we can use Gauss-Bonnet theorem, and it's easy to compute Euler characteristics, so we get the same number. And the third one is looks strange. This uses arithmeticity. So we look at the group PSL2Z modular primes and come up with a countable collection of finite groups of Lie type. And each of these finite groups, we can compute its order, and then we assemble an Euler product of these orders. And apparently, it gives us also the volume, which can be expressed as a zeta value, and so this in particular proves that Riemann zeta function of -1 is a rational number. I think this argument was first outlined by Sarah, but maybe it's long before. Okay, so, well, the message is that this strange way to compute volume is the only way that we can promote much further in higher dimensions and to other Lie groups. Because, well, it's, in higher dimensions, it's hardly possible to describe the fundamental domain of the group. Okay, maybe you can create an example of a fundamental domain in dimension 100. Even that is hard. If you want it to be of finite volume and discrete group. So it would be very difficult to do something like this in higher dimensions. And we also don't know Euler characteristics. But this method appears to be very powerful and robust in very wide generality. So in order to use it, we need to define the class of objects on which it applies, and it's going to be these arithmetic groups. So, well, here is a definition of arithmetic subgroup on an algebraic group, and the point is that if you haven't seen this definition before, I don't think I will explain it to you in 1 minute. It's about half an hour, I would say. And if you've seen it before, you know it very well. So I will not talk much about the definition. I will just indicate the connection with the previous example. So, look at SLN-Z. It can be written as an intersection of the group of rational matrices n by n with determinant 1 and this product, which says that, okay, these are p-adic integers, and each intersection there is a diagonal embedding here. So each intersection tells us that the denominators of these matrices should be not divisible by a prime p. And as far as we are running through all primes, the formula says that denominators are not divisible by any prime, so the entries are integers. Well, this is a pretty obvious example, but it can be generalized. So, for instance, instead of taking SLN ZP, we can change it over some finite number of places and put some other compact open subgroup over or p-adic group, and it will be still coherent collection, so it will define us some other principal subgroup. And we can get countable collection of principal arithmetic subgroups. Well, it's good, but the main point is that every maximal arithmetic subgroup is a normalizer of some principal arithmetic subgroup. And maximal means that it's maximal lattice. Now let me show what it has to do with the quotient spaces. So if we have a covering of orbifolds, well, in this case hyperbolic orbifolds, so O1 covers O0, then in the language of fundamental groups, it means that gamma 1 is so it inverts. Gamma 1 is subgroup of gamma 0. So if we're looking for some minimal volume orbifold, it means that we need to search for a maximal discrete subgroup. So we are interested in maximal arithmetic subgroups. And by the previous slide, they are defined by principal arithmetic subgroups. Okay, this is repeated here. So this is the setup, and celebrated theorem of Borel and Harshchandra says that arithmetic subgroups are discrete and have finite covolume. The discrete part is easy, but finite covolume is not obvious at all if you look at it, because okay, they may have cusps, for instance. So this is a deep result which is proved using reduction theory. But it doesn't tell you how to compute the volume, it just tells you that it's finite. Right? Computation of volume can be done using volume formulas. And here I will mention some of the volume formulas which we have. So the first I would like to mention Gauss-Bonnet theorem of Hager. Then there was a volume formula by Borel, paper of Prasad, and the paper of Gross. The volume formula of Hager applies to so-called split groups, and our groups are not split, so we cannot use Hager's theorem for the purpose of the hyperbolic orbifolds, manifolds. Borel's formula applies to it covers hyperbolic 2 and 3 of manifolds and their products. So it doesn't apply to higher dimensions, but in dimensions 2 and 3, it covers all arithmetic examples. Prasad's formula applies to arithmetic quotients of any simple groups, simply connected, and this formula is a big result which allows to handle the computation which I'm going to describe. So, the idea behind all these volume formulas is to generalize this computation that I showed before. But the generalization is highly non-trivial. And luckily, now we have these formulas, so we can apply them to geometric problems. I'm going to describe the application to hyperbolic orbifolds. There are several other known applications, and maybe quite a few which we don't know. So from the known ones, I should particularly mention the work of Prasad and Jung on classification of fake projective planes, which was Prasad's talk on the previous ICM. And I can also mention important application of the volume formula and this measure of complexity to classification of arithmetic reflection groups, but I'm not going to talk about it. Now I can show you the results. We have two theorems. Just a few words about how these results come out. So when I was a postdoc in Bonn, I wanted to find hyperbolic four-dimensional manifold of the smallest order characteristic. It's a well-known problem, and it actually comes from theoretical physics, so there is some interest in this example of hyperbolic minimal volume 4 manifold. And okay, I was thinking about this problem, and actually the answer to this question is still not known. But what I managed to do is I could reduce it to finite computation, but the computation doesn't look feasible. So there is a finite computation which can be done in order to answer this question, but it was not performed yet. However, I noticed that if one relaxes the situation and consider also spaces with singularities, orbifolds, then it becomes easier, and one can even find these minimal volume examples for arbitrary dimension, not only dimension 4. So this was my paper published in 2004, and there were some gaps and mistakes, and one conjecture in this paper, and the gaps were corrected in addendum, and actually I also managed to solve the conjecture, so there is an addendum to the paper which is important. Later, when I was working in Durham, Vincent Emery was starting his PhD, and he approached me with a question of doing the same for odd dimensions. So my paper of 2004 refers to the situation when the dimension is even, when in particular Euler characteristic is non-zero. So it was clear that the same technique works for odd dimension, but okay, nobody wrote the details, and we started working with Vincent, and apparently we found out that technically the odd dimensional case is much more difficult. And okay, with some hard work, in 3 years we made progress and eventually managed to solve this problem. It was Emery's PhD thesis and our joint paper. Now so the minimal volume for arithmetic orbifolds is completely solved in all dimensions. Okay, we did it for n equal at least 4, and the smaller dimensions are known before. The value of so there are two interesting features here. One is uniqueness of the minimal volume example, and another is that we actually can compute its volume. There is an explicit formula. Now I will show the formulas. So this is for co-compact case. You can see Z and L values that naturally feature in these formulas. And okay, there are also some rational factors and multiples of pi. These formulas are a bit long, and there's also non-co-compact version. I'm not going to explain all the, okay, basically it's elementary formulas. The point is that they are precise and you can do computation, and you can also do an estimation of the growth of the minimal volume with dimension, and you can do comparison. You can compare co-compact and non-co-compact, and you can do various things. So the formulas look frightening, but they are apparently useful. Before telling more about the formulas, let me just say a few words about the proof. So the key element of the proof is, as I said, Prasad's volume formula. And then there are some tools from algebraic groups theory, mainly Roatis theory to control the local structure, and Gauss cohomology allows us to define, so it's used at least 2 times. First, it's used to control the index of the principal arithmetic subgroup, which I understand very well in the maximal arithmetic subgroup. And secondly, it's used to prove uniqueness results. So you saw that all these extremal examples appear to be unique. And in order to prove the uniqueness, we use algebraic groups. Unique up to isometry. And there is some number theory which comes out when we actually prove that the bound is optimal. So the whole strategy of the proof is as follows. You create some arithmetic subgroup, which can be easily done using quadratic form. You find arithmetic subgroup in any dimension. Then you compute its volume using Prasad's formula. Then you look at the formula, and there is some optimization procedure. So you can change this arithmetic subgroup so that the volume becomes smaller. And you optimize through a few steps, and at some point you notice that it looks like there is nothing else you can do. And then that is the point when we start to prove that it's actually the optimal solution. Apparently during this optimization procedure we had a few surprises. Like the first example which we started, which we thought would be optimal, appeared to be not optimal. So I first thought that it should be defined over cubic field, but it appeared to be defined over quadratic field. And also there are some interesting features, in fact, appearing particularly in dimension 7 and 19, I think. And so there were some surprises which this procedure gave, but at the end, so one has to prove that it's optimal example, and the proof uses machinery from number theory, like various discriminant bounds regulators and so on. Okay, now let me remind you the formulas. These are here. we can plot them in Mathematica and get reasonably nice picture. So this, there are two plots here. Here is the dimension, so dimension goes from 2 to 30, and the first plot is the volumes of non-compact orbifolds, and the second plot is the volumes of minimal volume compact orbifolds. So the first quite surprising thing which you notice is that the volume of, okay, in small dimension, there is no surprises, but when dimension grows, the volume of non-compact one becomes much smaller than compact one, and the difference grows. So apparently, the orbifolds with cusps tend to have simpler structure than if you don't allow cusps. And this is a very interesting geometric phenomenon, I think, which can be explored more. It first appears in dimension, okay, I will show it later in dimension 6. But here the difference is really small, but if you go to higher dimensions, then the difference becomes really dramatic. So from this picture, we can get some corollaries. And okay, the pleasant fact is that you can notice something on the picture, and okay, you can write it as a conjecture, but then these conjectures appear to be very easy to prove because we have these formulas, and it's not hard to make estimation. Like the formulas are complicated, but then you estimate and okay, you prove results like this. So they kind of come for free. Uniqueness was already mentioned. Here is the first corollary that the values of the minimal volume and also the ratio between volume of compact and volume non-compact grows super exponentially with the dimension, extremely fast. Here is another corollary that for even dimensions, at least 12, and later it was improved to 6 by Emery in his paper. There is no orbifold or no manifold with order characteristic 2, so there are no arithmetic rational homologous spheres in these dimensions. And in dimension 4, this is still open. And it's the same computation which I mentioned, which was never done. Okay, and one more corollary says that what I also mentioned, that for high enough dimensions, the compact tends to be bigger than non-compact orbifold. In fact, the last corollary has even better view if we restrict to manifolds. So if there are no singularities, then the conjecture is that only in dimension 3 we can have compact orbifold, manifold, hyperbolic, which is smaller than any non-compact. And that one is obtained by dense surgery. In other dimensions you cannot do dense surgery. And apparently, well, okay, this is conjecture. We have some evidence for this conjecture. It's true for small dimensions, and it's true for sufficiently large dimensions arithmetic manifolds. This is another joint work with Emery. Okay, now finally I come to the part when I don't want to assume arithmeticity anymore, and let's see what we can do in this case. So in this case, there are two ways known to me how to bound volume from below. One is using doing quantitative version of Cartan-Margulis theorem, and another way is to use Margulis lemma. So, well, I still have time. So Margulis lemma says that you can decompose. Okay, this is Margulis lemma for it's again some fact true for all the groups, non-compact, and they're discrete subgroups, but we are interested in groups of isometries of hyperbolic planes, so here it simplifies a bit. So it says that if you look at the quotient space, it says that the quotient space can be decomposed into a thick part where injectivity radius is bigger than Margulis constant, which is constant depending on the dimension, and thin part, which looks like cylinder. Now, this lemma immediately tells you that if you look at the hyperbolic manifold, then its volume is going to be, in dimension n, is going to be uniformly bounded below by Margulis constant. It's a very tricky task, in fact, to extend this to orbifolds, because, this was done by Gylander and this is the result of Gylander. So he used Morse theory to push this result from manifolds to orbifolds, and it works with slightly worse constant. So it's not exactly Margulis constant. Here is the volume of a ball. This nu of r means volume of a ball in hyperbolic n space of radius r. Okay, but it's It's still a positive number, which is defined by Margulis constant, and it can be computed. So there is a bound, lower bound on the volume, which works for orbifolds as well. Okay, when you look at this bound, and you remember that we try to understand what happens in higher dimensions, maybe the first natural question comes to mind is how Margulis constant behaves when dimension grows. And it's a very interesting question, in fact. I was thinking about it, and then I talked to Misha Kapovich a year ago, and he told me an idea how to prove the following proposition. So the proposition should be attributed to Kapovich. There exists a constant such that Margulis constant is bounded from above by c divided by root n. So the proof of the proposition you can find in my proceedings paper, and it uses geometric group theory. In particular, it implies that Margulis constant goes to 0, which is not when n goes to infinity. However, this result has some feature. So there are some open questions around this result. So we prove it. So the proof uses discrete subgroups, which are not lattices. They have infinite covolume, because Margulis lemma is for all discrete subgroups, right? So we don't have to use lattices. So we construct using some clever procedure appearing in previous Misha's paper, can construct discrete subgroups of. You see, when you start to think about it, you want to prove that when dimension is large, Margulis constant can be small, but you're always at risk to prove that when dimension is fixed, Margulis constant can be arbitrarily small, and this is not true. So at some point in your argument, you have to use the fact that you're allowed to go to higher and higher dimension in order to make it small. But it works, and it gives this bound. The lower bound for Margulis constant are much smaller. They decrease super exponentially with them. But I believe that this is actually about the right behavior of constant. However, I don't know how to prove it. And it's also, it may be possible to show that for you can achieve the same kind of phenomena using non-arithmetic lattices. For arithmetic lattices, there is a well-known conjecture which says that Margulis constant should be, if you restrict to arithmetic lattices, then Margulis constant should be bounded uniformly from below. This Lemmer's or Margulis implies. But for non-arithmetic lattices, it may be possible to produce similar examples. However, we thought and we didn't manage. So it's an open problem. Now I'm getting to the final slide. So, here is the lower bound for volume, and it's computable. So if you compute it, you see that it decreases very quickly with n. super exponential decrease, you know, for applied mathematics, it means that it becomes 0. Some function which decreases super exponentially is 0. But okay, for pure mathematics it's not 0, but it's something which decreases incredibly fast. And now, well, there is about okay. The similar computation can be done using quantitative version of the proof of Kazan-Margulis theorem, and it also gives the same super exponential decrease. Now the conjecture, well-known conjecture, is that the minimal volume hyperbolic orbifolds are arithmetic. This is known to be true in dimension 2 and 3, and okay, not known in high dimension. So if the conjecture, minimal volume conjecture, is true, then the actual growth rate of the volume with the dimensions should be super exponential growth, and what we know only is super exponential decrease. So this indicates that there is still a lot of we want to understand about volume. Yeah. Okay, that is basically how it is. All right. Here is a picture from a paper by Felix Klein from 1979. Which shows the tessellation, part of the tessellation of hyperbolic plane by the triangles with angles 2, 3, and 7, and this is the minimal volume plane, minimal co-volume plane tessellation that, for instance, appeared also in the paper by Siegel.
Questions and comments?
Your examples were, these minimal examples were all defined over the same field, independent of n. Is there a good reason for that?
Yeah, there is an arithmetic reason for that. Actually, if you go to dimension 2, then this Hurwitz group is defined over a different field. And when I first started, I thought that field were here. But it apparently changes and stabilizes immediately. There is a simple arithmetic reason. So the fields which come out are the fields with the smallest discriminant. Well, okay. If you allow cusp, you allow rational numbers and discriminant 1. If you not allow cusp, the smallest discriminant is this field q square root of 5. And discriminant appears in volume formula as a term with a high power. So, well, in higher dimensions, it's very easy to see that it dominates the rest, and in lower dimensions, it's a lot of high wrong.
You say the minimal volume is got arithmetic groups coming from quadratic forms?
Yes. Well, this is also part of the result.
Sorry?
This is part of the result, right?
Yeah.
Because we had to consider all the cases.
From an arithmetic point of view, it should be possible to define p-adic volumes, especially large primes of hyperbolic manifold. Has this been done?
Volumes.
Because the manifold defines an element in the block group or algebraic theory. And there's a regulator which gives the volume. There's also a p-adic version of this.
That's interesting.
Indeed, there should be a notion of p-adic volume.
Yeah, that's an interesting question. I don't know any results, but I mean, it's something one can look at, but I didn't try it.
So let's succeed. So our last talk will start, since we are a little bit catch up, we'll start like